Hello, everybody. I'm Phil from Element 14 Community. Thank you for joining us today on the 29th of September, or even on the VODs. Today, we have James Hughes, Principal Software Engineer at Raspberry Pi. Hi, James. How are you doing? Thank you for joining us.
Hi, very good. Thank you.
Good. So for anybody that's never used this platform, we're on 24 here at Element 14. You can submit a question on the box on the left-hand side. That is a live box. We will be taking them on. Hello from Robert, who's just saying hello. Gabrielle saying hello. Welcome in. The question box is live. We will try ask them at the end if we have time or during if they're relevant. The way this platform works is you can click and drag any of the windows to any size you want. So if it doesn't quite work for your device, you can just drag it and off you go. On the right-hand side, we do have URLs over to the Element 14 community and Raspberry Pi's documentation. So you can click through and learn a little bit more after this. We do have a series of Raspberry Pi ebooks that you can go and download for free with the same registration you used to get here. We have John, we have another John, we have Moyad, all coming in and saying hello. So thank you very much to everyone saying hello in the Q&A box. This is all live for your attendance. You will also get a certificate if you just answer the very simple questions below in the quiz. But other than that, I'm just very excited to hand over to James because I'm very, very excited to hear more about the RP2040. James, please take it away.
Well, thank you very much, Phil, for that introduction. My name is James Hughes. As was stated, I'm a principal software engineer at Raspberry Pi. I'm not the principal software engineer at Raspberry Pi. I'm just one of them. There's a lot of very clever people here who can claim better titles than that. I'll try and quickly go through who I am and what I do here. I've been working for Raspberry Pi, I think it's about 6 years now, maybe coming up to 7. But I've been involved since actually before the first Pi was released. So I worked at Broadcom with Eben, not in the same team. I was in the applications team there, but then I got involved and was helping out in the forums. So I've been volunteering for them for a long time before I actually joined the company. I was sort of, what have I done since then? I was the first person to get a Bluetooth adapter working, GPS adapters, and this was on the actual prototype boards, not on the actual release boards. I'm the software engineer who wrote all the Raspberry CAM applications as well. So Raspberry Steel, Raspberry Vid, that sort of stuff. That I did while I was volunteering. Since I joined the company, I've been a bit of a all-rounder, no specific target area, but I've worked on the multi-monitor support, LCD panel sorts, all sorts of things. And now I work in the applications team, which is a team that's only been going for about a year and a half. Actually part of the hardware side of the company, although I am a software guy. Hardware just goes over my head most of the time. So what do we do in the applications team? Well, we're really a technical support team for industrial customers, although we do obviously veer out into other areas as well. I write software for the production lines. I run the Powered by Pi program. For those of you who are familiar with that, it's a useful program if you've got a product that uses a Raspberry Pi of any sort, RP2040 or the main Pi range. We help out with trade shows. We were at Embedded World earlier this year, which went really well for us, gave away 25,000 Picos, which I'll talk about them a little bit later. And we've just had a recent partner event where a lot of our resellers, design partners and things came along, and they had a good time as well. So what do I know about the RP2040? I haven't spoken about that yet. I was involved quite early on writing some very early test software when the ASIC team was still designing the chip. I wrote some of the functionality in the SDK. I did all the Doxygen comments in the code, so there's an awful lot of Doxygen in there that's you can blame me for, and quite a few of the example code, usually to do with little LCD displays and that sort of thing. So that's my Pico. Oh, I also wrote the Pico project generator, which is a thing to try and make it easier to start a Pico project. I won't be talking about that during this one. So that's me. I should have put that slide up, I suppose, but there you go. I got the date wrong, unfortunately. So let's start. Let's talk about the RP2040. So what is it? Well, it's a microcontroller. So if you ask 10 engineers what a microcontroller is, you'll get 10 different answers, I suspect. The way I look at it and the way we look at it here, it's a computing device that connects the world of software to the world of hardware. So allowing software developers to write software that interacts with the physical world in the same sort of deterministic, cycle-accurate manner as digital logic would. So they're sort of in the bottom left-hand corner of the price-performance space. Microcontrollers outsell main big processors by a considerable amount. They're the sort of workhorses that power the digital transformations. And the RP2040 is our first microcontroller. What we hope it does is bring our values of very high performance, low cost, and ease of use into that microcontroller space. So that's a very brief introduction of what I think a microcontroller is, and I'm sure you guys and girls have a very different idea. But let's quickly talk about the RP2040. The name of it, really, RP, that's fairly obvious, Raspberry Pi. 2 stands for the number of cores. The 0 stands for the type of core. In our case, we're an M0 plus. The 4 and the 0 at the end are both memory sizes. Not an obvious memory size. That's based, the calculations there on the slide. So 4 means 256K. In fact, it's a tiny weeny bit more than that, but that's what the floor is for. And on the RP2040, like I said, 256K, but we don't have any non-volatile memory at all on there, so no flash or anything. Might like to look at a quick picture, quick X-ray of the chip itself. It's quite interesting. I was looking at this only this morning and thinking to myself, cool, aren't the processing cores are tiny compared with almost everything else, and I find that quite extraordinary. The SRAM is obviously the real big ticket item on the die itself, but you can have a quick glance around and see what all the other bits and pieces that I'll be talking about later on in this talk. So you can tell that it's actually quite a large amount of memory. I think we're not unique, but it's quite unusual to have so much memory on a microcontroller, and that's one of our unique selling points, let's say. So let's have a look at a bit more detail of actually what's on there. This is a sort of a block diagram of the device. We will be going into a lot of this stuff, not in a huge amount of detail. Unfortunately, you can't. There's a week's worth of training course, I reckon, on the RP2040, which we're trying to squeeze into an hour. So we can't go into massive detail on most of this stuff. I'll try and give an overview of a lot of these things. But one thing you can note from here, this isn't just a powerful chip. The M0 cores are quite powerful, and we clock them very highly for the design. But the bus fabric and the peripherals around that are designed to really give you a very high performance. The RAM itself is in 6 independent banks. We have a connected switch to the bus fabric in the center there. So it means that all the cores are arranged around that, and a lot of stuff can run in parallel. The DMA engine can run in parallel. So it's a very, very high performance processor, especially at the price we sell it at. That's for those of you interested in the bus fabric, it's a fully connected AHV crossbar for those of you that are into their ARM processors. So how do we package it? Just one package at the moment. It's a 7mm by 7mm QFN. The device itself is 40 nanometer, which is pretty small, not as small as you can get. Some of you may be thinking, well, 40 nanometer, isn't that one of the processors that has supply chain problems at the moment? Not for us. Whether it was excellent planning or luck, we have ordered a lot of dies up front, and they're waiting to go. So we can make, I think, by the end of the year, we can make up to 20 million devices. So we're in very good supply situation with regard to this particular device. Not so good on the other stuff, the Pi 4s and things, but this particular device is in very good supply. We've recently re-qualified it to a higher temperature range. So you can see from here, we're qualified now from -40 to +85. We had a lot of feedback that said with our original temperature range, I think we went from 0 to about 70. We need an extended range. So we did that testing, we qualified it, and now it can run at those extended temperatures. So that's good news. I won't dwell very long on this one. It's basically just a little comparison of the RP2040 with some other cores, with other microcontrollers, all with a very similar M0 cores. But you can see that a big difference here is the speed with which we run the device. 133 megahertz is the qualified top speed. We actually send it out by default, or the SDK runs at 125 by default. We have a lot of RAM compared with some of our competitors. We have some secret sauce called the Pio, which I'll go through a little bit later. Similar sort of GPO sort of stuff, and some other peripherals there that I will sort of briefly go through a little bit later. There is one thing at the bottom there that you will see. We're very cheap, but the one above it, do these other cores run Doom? Well, we do. It's a funny benchmark to use, but the guy who designed the SDK is a very, very clever chap, and he's actually got a port of Doom running on this microcontroller, which is really quite an impressive feat. It's all blogged on his blog. So if you want to look at that, then it's well worth a go to see how he's used all the features that are available on the RP2040 to speed things up so much that he can actually both generate VGA video, plus the sort of simulated 3D that is required to run Doom. So that's quite an impressive bit of work that's well worth looking at, just to give you some idea of the performance levels that we can get out of the RP2040.
James, with Doom, so for anybody in the audience, this is the second webinar we've had in this series. The other one will be linked below and is linked on the event page. Roger, who hosted the first one, showed a demo of Doom running and a video of it. So if anybody hasn't seen the first webinar, please go back and watch that, and you can actually watch Doom running. That's my only interjection.
No, that's absolutely fine. A lot of people who will have seen Roger's one will have seen we've had some duplicate slides. Hopefully, we'll start getting a bit more interesting for those people in a few moments. So, how do we design for the RP2040 itself? As with a lot of our stuff, we provide a reference design. Is that rendering you see on your display at the moment? That is the reference design, a minimal design example. All the KiCad files are available there. They're available actually on our product information portal, our pip.raspberrypi.com. This contains all of our publicly published documentation, except for some data sheets, which will end up in there eventually, but they're not there at the moment. The data sheets are at datasheets.raspberrypi.com. There's a huge amount of information in there. One of the plaudits we had when we launched the RP2040 was the quality of the documentation. It really is good. I probably should have said I did do some of that early on as well. So, that was a very much our documentation team and the engineers involved. So what you're doing when you're reading our documentation and our data sheets is you're reading what the engineers actually wrote, which is pretty good. Right. Okay. So that's a quick glance at designing. We'll do a little bit more on that a little bit later. Programming. Here's a bit of an animation for you. So the obvious or the easiest way of programming these things is you plug them in while you're pressing down the boot select button on the Pico. We'll come to Pico in a moment as well. It appears as a mass storage device, and you can just drag your compiled code directly to the Pico. It will reboot itself, and in this case, this was a blink and light demo, so that sort of happens and reboots itself and starts up automatically. So it's a very easy thing for beginners to get into. You just plug it in with the boot select button pressed down. It appears as this mass storage device. You just drag and drop your code to it. Now, there is an alternative way of doing it, which we'll come to a little bit later when we talk about debugging. But really easy to use. So I've mentioned the Pico a couple of times. This is our development board, effectively, although it is used a lot by third parties. Actually, as is, they've built them into other products. Rather than using a bare RP2040, they can use a Pico. It provides a huge amount of it means you have to do less work. You can just solder it down to a circuit board, and then you can see we have castellated pins all around the outside, so it can be soldered down. It's why it's flat underneath as well, so it can just sit down on your own circuit boards. So that's the Pico. We very recently launched the Pico W. So there's a picture of one of those, again with the same castellated PCB around the edges to make it easier to solder down. But this one has Wi-Fi. This has been a really good seller as well, competing with some other products out there in the market that have Wi-Fi built in already. This one's up to $6, but for $6 you get the RP2040 and you get the Wi-Fi. It's an 802.11b G and N Wi-Fi chip. And the important thing about this is that it's a modular approval. You can see that the device has a little can on it. I think that helps in getting this sort of approval. And it means that that approval goes into the product that you put the device into. So you don't have to then go through the quite difficult process of getting your device, the device compliance that you need in order to sell into other markets. That modular approval. That was again something that came from the feedback we received from customers on the Pi Zero and the Pi Zero W. That sort of those devices with the Wi-Fi. People wanted this modular approval, so it made it so much easier to get their devices qualified perhaps in the markets they want to sell. So we haven't mentioned about programming these things and what languages that the Pico goes. I'll very briefly. So it's C, C++. We provide C and C++ and MicroPython. And we saw from the drag and drop example earlier how easy it is to get from that sort of code from your code base built and then onto the devices. So, but there's MicroPython and various other things that I'll briefly touch on in a moment. So where do we get these? Well, we're on a Farnell webinar here, so that's a good place to get them from. Just Farnell, one of our distributors, so you can buy them from there. We also sell these devices direct, actually, but only to business customers. We sell them in reels. You can see on the little screenshot on the left there. That's a small reel there, and you can see how we sell them in that format. The reels come in, I think, at 3,500 sizes. And you get the prices down in quantity to a little bit below that 70 cents we see on the slide. So if you really buying large quantities, the device itself, I think, will drop almost to 50 cents per device. So given the performance that you get, I think that's really quite a lot of bang for your buck there. So basically, get it from any of our resellers, Farnell, resellers, or from Raspberry Pi Direct if you're a business customer. I should add actually that the Pico is also available now in this sort of reel, basically the same plastic sort of format, cellophane over the top in a big reel, so you can buy Picos as well if your product is using the entire device. Okay, so let's we've done a bit of a sort of quick preview of the device and where to get it from, and sort of brushed over a lot of things there, I think. So let's have a slightly deeper look into what the device actually has on it. So I2C, all devices have to have I2C. It's a bit of Synopsys IP in there. It's worth noting that nobody or very few people design processors entirely from scratch. They're generally bolted together from intellectual property IP from third parties. So in this case, the I2C block comes from Synopsys. It could be a master or slave device. Either of those I2C peripherals can be a master or a slave. So you could actually have it as a master talking to some downstream IoT sensors perhaps, but also as a slave upstream. Standard mode, fast mode plus, 10-bit addressing in master mode. There's also transmit buffer there, a 16-element transmit FIFO type of thing, and both on the transmit and receive. And it can be driven from the DMA. So using it can be extremely efficient. It's also could generate interrupts, as you would expect. The SPI, again, 2 peripherals. This is a Motorola compatible, well, Motorola, National Semiconductor, Micro, Texas Instruments serial interfaces, which covers the vast majority of the market. Again, either of those SPIs, I believe, can be master or slave. The PWM. Now, this is a block that we did design ourselves, and there are 8 what we call slices. You could call it a slice or a block, and each slice can drive 2 PWM output signals. But what's quite interesting about these devices, they can also be used to measure the frequency or duty cycles of input signals as well, because they have an input line. So that they're quite the guy who designed it, I had to get him to explain how it all worked. And it's really quite a sophisticated system. You think PWM is just pinging a line up and down, but actually these ones are quite clever and well worth looking into. So with 8x2, we've got 16 PWM controllable PWM outputs, and which can be spread all over whichever GPIO is on that you want. UARTs time 2. Everybody knows what a UART is. Pretty standard IP block there. One thing to note, the Pico is a 3.3 volt device. So if you are plugging in UARTs, make sure you're at 3.3 volts, not 5 volts, which some devices do. So you don't want to blow up your Pico by plugging it into a 5 volt UART. Timers. So there's a global microsecond time base on the system. It generates interrupts based on this time base. So it's a single 64-bit counter, which is incremented once per microsecond. This is 64-bit. Remember, the M0 is a 32-bit core, so we have to have some latching registers to read it. So when you read the low byte, the low word, the low 32-bit word, it locks the upper one so that you don't get any sort of race conditions when reading those 2 peripherals. There are 4 alarms on the device. Hold on, I've got to read on my laptop. So it's 4 alarms on the timer, which you can use to interrupt at whenever you want. Note that they only work on the lower 32 bits, those alarms. So I think that gives you 2 or 3 days worth of look ahead on the alarms. There is software in the SDK if you want the longer alarm delays to deal with that.
We have one quick question, which is relevant at the moment from Ralph. Ralph's asking what the real-time clock accuracy rate is for the RP2040. I'm sure we could send Ralph to some specs, but I don't know if you know it off the top of your head.
I don't know how accurate it is offhand, I'm afraid.
Okay, thank you very much.
I was going to briefly mention the RTC in a couple of minutes, but yeah. But I didn't have that information in my bit of data, so I'm afraid I can't help with that one. Well worth asking. It's worth saying at this point that if you do have any questions that I can't answer today, try our forums. There's a dedicated Pico and RP2040 section on our forums. If you don't get answers there's an email address coming up at the end of the presentation to talk directly to us in the applications team.
And obviously, to throw my own marketing in there as well, you can ask in the Element 14 community, where we have over 850,000 engineers who are always up for answering questions.
Yeah, absolutely. There's a lot of information out there in the old internet. Okay, so we were talking about the timer. It's actually a 1 microsecond reference generated by the watchdog timer, which in turn derives its input clock from the reference clock, which is usually directly collected to the crystal oscillator. So it's a bit of a pass to get down there, but that's how it works. One thing to note, 64-bit counter, because it's a 64-bit counter, it effectively cannot overflow. I think it's over 1,000 years at the 1 megahertz refresh rate, so it's never going to overflow. So effectively, it's monatomic in practice. On the RTC, we mentioned that just now with the question on the accuracy. As I said, I don't know the answer to that offhand, but it's worth noting that the RTC, the Pico and the RP2040 themselves don't have any sort of battery backup. So if you are going to use an RTC and want to retain the clocking over a power down, that you have to sort of incorporate some sort of battery system on your device. So it's worth remembering that. So again, the RTC has an interrupt function or alarm interrupt that can wake the processors up, and also wake up the clocking, the crystal oscillator or the ring oscillator on the device, to wake them up from what we call dormant mode, which is our low power mode. I think it's worth mentioning at this point that this dormant mode is not that low power. It doesn't. It's we can't compete on the low powerness with some other devices out there. This is something that we've taken on board, and will fix in any possible future devices. So, that's definitely something we're looking into. Right, the ADCs, the analog to digital converters. We have a single analog digital converter which is muxed over 5 inputs. 4 of those inputs go out to the GPIOs, and on I think 26 to 29 or something like that. One input, the 5th input, stays internal to the device because it's attached to an internal temperature sensor. So effectively, we have a 4 inputs, 4 ADCs. The sample rate by default is 500 kilo samples per second, running off a 48 meg clock internally. This can actually be overclocked. I've very recently, only in the last couple of days, saw that somebody had got up to 1.5 megahertz, 1.5 meg samples per second by overclocking the device. So that's quite interesting. It's a 12-bit ADC. There is a gotcha in the ADC. After the device was launched, we found a problem with very specific values going into the ADC. But I won't go into what the actual issue is. It was to do with the capacitance in the FPGA was slightly needed to be changed slightly for the actual chip. But this is all covered in the errata in the documentation. So check out the data sheets. That's in section 4.9.4, I think. So that would describe where the issues lie with the ADC. But for the vast majority of people, it's you can ignore it.
There's quite a few people interested in the ADC. Sorry to cut you off there. There's a little bit of delay between us. So I believe you might have just covered that, but Susan asks, has the ADC data reading spike issue been addressed? I believe that may be what you've just been referencing.
Yes, that is exactly the case. We haven't respun the chip just to change that. It's a very expensive business to respin a chip like this. So at the moment, that errata is still present in the chip.
Okay, and then there's the one which I'm going to phrase more as a request. Alzandi says, we need more ADCs. Have you got any more planned for the future? So I think that's consumer feedback.
Yeah, that's an interesting one. I will take that to the ASIC team. I will ask them. Obviously, as everybody knows, we never discuss future products until they come out here at Raspberry Pi. But certainly, we do pay an awful lot of attention to what we hear and what we read and how people comment. So these are all interesting feedback for us. So and it does get fed back to the ASIC team. It gets fed back to Eben, even who basically decides everything. So that's good feedback. Thank you for that.
Thank you.
Okay, so that's a very brief whiz through the peripherals, the main ones. So, but there's 3 other things interesting here. The execute in place cache. Now, this allows external flash memory. As I said earlier, there's no flash memory on the device. So if you're building your own board, you have to incorporate your own flash memory. It's QSPI. But the execute in place stuff is really quite interesting. It allows external flash memory to be addressed as though it was internal memory. So there's bus reads in the memory window are translated into a serial flash transfer, and then the result is returned back as if it was a memory read. So this process is entirely transparent to the cores, to the M0s. So the processor can actually execute code directly from this flash memory. It doesn't need to be loaded into RAM first, hence the execute in place. Another advantage of this is that the that can be cached. So we have a cache in there. You've seen it in the block diagram and on the Xray. And this accelerates the average bandwidth and improves the latency when reading flash to not quite as fast as to running it from RAM, but a very, very good performance boost by using the caching over the executing place. Okay, let's SIO. This stands for the single cycle IO block. This is a little block. This is one of the bits I wrote some test software for right at the beginning of the project. These are peripherals that require low latency deterministic access from the processor. So they're accessed via the M0 Plus's IO ports, which is an auxiliary bus port, and so they can perform extremely rapid 32-bit IO read and writes. And so what the SIO provides is intercore FIFOs. We're a twin-core device. You need some way of talking between the two devices. So we have intercore FIFOs. There's 32 hardware spin locks in the SIO block. Also, some integer dividers. So there's actual hardware to improve integer divide performance. And there's also 2 interpolators. These are, well, a good example is the Doom stuff, where the interpolators were used as part of the 3D rendering system to interpolate between values. So the software engineer who did that used all the parts of the chip to try and improve performance, right down to using these interpolators in the SIO. The SIO also handles things like GPO setting and clearing monatomic GPO stuff. So quite a useful little block there. Right, so the last one on this slide, we've spent quite a lot of time on it so far, but this is the PIO. Now, I'm sure a lot of people are quite interested in the PIO. This is one of the secret sauce parts of the chip. It's 2 programmable blocks there, which are exceptionally specified towards I/O. Let's have a quick look at a block diagram of how this sort of bolts together. So the PIO is dedicated connections to the bus fabric, to the GPO and the interrupt controller, so very, very deterministic. And why do we have it? What's it there for? Well, interfacing with other digital hardware is hard. It happens at very high frequencies due to the amount of data that needs to be transferred, and has very, very exact timing requirements. And PIO is our response to the problems of bit-banged interfaces, really. You can do that sort of thing by just programmatically pinging GPIOs up and down. But then you're right, the code is very complex and at the whim of something else happening in the system. I'm not going to go into a huge amount of detail on PIO. There's a spectacularly good explanation by the guy who designed it in chapter 3 of the Pico SDK datasheet, and that is well worth reading. I will go into a little more detail, but I'm trying to get that in first because just to remind you that our documentation is very comprehensive, and this is an area where it's very difficult to describe how this all works over a 1-hour presentation. But anyway, there are 2 identical PIO blocks in the RP2040. And the PIO is it's programmable in the sort of same sense as a processor, so you can program it to support various I/O standards. So we've already got examples for 8080 and 8000 parallel buses, I2C, I2S, SDIO, SPI, DSPI, QSPI, UARTs, DPI, VGA, that sort of thing, all driven by this PIO system. And remember, this is independent of the actual dedicated hardware for things like I2C and SPI that we have on there as well. Each PIO block has 4 state machines, and each one of those can independently execute sequential programs to manipulate GPIOs and transfer data. But unlike a general purpose processor, they're very, very highly specialized towards I/O, with a very, very determined focus on determinism, precise timing, and very close integration with the other fixed functions in the hardware. So we make these state machines programmable in a software-like manner. We didn't want to do something like CPLD, a complex programmable logic device, because because of the complexity, we wanted them to be software controllable. The PIOs fit into a sort of similar sort of area as putting in a CPLD, but because they're programmable, they can be reprogrammed to do whatever you want. So that's really why we chose to take this route. So each one of these state machines is responsible for setting and or reading GPIOs, buffering data to and from the processors or from the DMA subsystem, and telling the processor via IRQs or for polling when data is arrived or when attention is needed. So it presents quite a familiar programming model, quite a simple tool flow. It's not easy. I'm not by no means an expert on this, but it is very, very performant, very, very flexible because of the way that it's been designed. So, for example, we can actually output DPI from a PIO. You use a couple of a couple of the state machines to drive it, and we can get 360 megabits per second out of PIO, deterministic megabits per second. During the active scanline periods, that's running for a 48 meg system clock. So in this particular DPI case, and all these are available as examples in our GitHub repos. One state machine handles frame and scanline timing. One generates a pixel clock, and another one generates the pixel data and unpacking run length scanlines. It's really quite something to see that this tiny little core with the addition of these POs doing things like DPI. So all of these statements. Oh, sorry, go on.
Oh, no. Please finish up. We have one question about the PIO state machines as well from one of our top members. Whenever you're ready, as well, please finish up your thoughts.
Okay, I've just got a couple of pages on the PIO, and then I'll try and answer the question. So all the inputs and outputs can be mapped to the GPIOs, which is 30 on the 2040. And it's all completely independent and simultaneous. So you've got one PIO state machine talking to one GPIO and another one to another one. There's no sort of contention between the two. So we talked about it being programmable. It only has 9 instructions. And you might think, how on earth do you write a I2C system in 9 instructions? But actually, they're quite clever instructions. You can see there's not very many: jump, wait, in, out, push, pull, move, IRQ, and set. But we have things like each instruction could be modified. We have delay and side set stuff. It's worth noting that each one of these instructions is exactly 1 cycle long. So that gives us this determinism, just 1 cycle per instruction. So they can be modified with the delay and side set functionality we see in this table. And what does that actually mean? You can specify in each state machine how much of that bit field is delay, how much is side set. So what is a side set? I mentioned it 2 or 3 times, but it can assert a constant value onto some GPIO. So may have an instruction like jump, but while the jump's happening, it will also set a GPIO or multiple GPIOs. So some of those 5 bits will be delay, some will be side set. So the delay is basically after the instruction is executed, then a delay for a certain number of cycles. So you can see how this minimal set of instructions can actually be quite sophisticated. So we also have, somewhere in there, we have auto push and auto pull. Now, we have the push and pull instructions. They are for pulling data to and from the M0 cores into FIFOs that feed into the PIO. But we can do that automatically. This is just because it's such a common operation, we put in a special bit of hardware in the PIO that means that when it gets to a certain point, if a buffer becomes to a sort of semi-empty, it's nearly empty, it can be automatically filled up by the hardware, so you don't actually have to write certain instructions, which is useful because actually each state machine, or each PIO block, should I say, only has 32 instructions, and you have to spread that over all the state machines in that PIO. But when you consider the complexity you get out of just 4 or 5 instructions, then whilst it might sound like a bit of a limitation, it generally doesn't appear as a limitation in practice. So there's some clock dividers in there in the PIO as well. Generally, these processors run much faster than your communication system might want to run. So we can divide out the clocks, very accurate clock dividers, to make sure that if your processor is running at 125 megahertz, actually the PIO divides itself out and can run much more slowly for the slower communication protocols. This is a 16-bit integer 8-bit fractional value, so it can actually divide out extremely accurately. So a little bit on how we actually program the PIO. We've written an assembler that takes these instructions. We have a lot of boilerplate library code that you can, once you've got your instructions compiled, which just comes out of our make system, it uploads the programs directly to the PIO, starts them running, and all that sort of thing. So we've tried to make it as easy as possible to get these PIO programs into the system. As I said earlier, it's not easy to write PIO programs, but once you get the hang of it, they are extremely powerful. We've already implemented some useful ones anyway, things like UARTs, SPI, and I2C. We've already written PIO programs to do that. So if the two I2Cs or the two SPIs or the two UARTs aren't enough, you can then leverage the PIOs to add more of these if you want to. Right, what was that question, Phil?
So from Shabazz, who's one of our top members on the Element 14 community, who's very interested in this and working through it. When or if will there be a complete simulator available for the PIO state machines? There's a bunch on the internet, but it's unclear if they're entirely complete in the simulation. It's something people want to see, apparently.
Okay, that's an interesting question, and I did see it actually up front, and I completely forgot to talk to the guy I wanted to talk to about it, who would have been able to tell me whether we're planning one. As far as I know, we're not planning one ourselves. I do know that there is at least one net-based one that, as far as I can tell, is pretty good, but it's not something that I'm aware of. We're working internally on.
Okay, thank you so much. And we have a couple of really quick ones on PIO. It's very people are very interested in it. Is it specific for the RP2040, or do other ARM MCUs have it as well?
No, this is a very much specific to the RP2040, the Pio Blocks. It was something that was developed in-house by our team here, including one very, very clever chap who's basically started as an intern only a few years ago, and is now doing that sort of thing. So really high quality ASIC design and software design work. So he's in his mid-20s, I think, now, and obviously much cleverer than I am.
And I'll give you one more before I let you carry on, if that's all right. Alexander asks, should the PIO be programmed each time when the chip is powered, or is it saved in some sort of non-volatile memory?
Yes, it's programmed each time you start up. So your code will just upload it as it starts up.
Thank you so much.
Yes, it's effectively stored in your program binary in your flash and will be uploaded when you start up. Yeah. Okay, I've just noticed that I'm whizzing through the time, and I've still got loads of slides left, so I'm gonna speed up a little bit. What about the software? So we've talked about the hardware. What about the software? So we provide a C and C++ SDK, which is really just a very thin layer over the hardware. We don't want to provide too much sort of heavy-duty code. There are some areas where we have done so, where we want to provide some features that are available on other devices or other systems. So, excuse me, but it's mostly a thin layer over the hardware, so very shallow, just effectively, rather than having to write to a register with bit patterns, we'll provide a very simple C API that converts the parameters of a function into those bit patterns, so you don't have to. We're CMake based, which was an interesting design choice. Some people disagree with that, but I'll go through why we chose that in a couple of seconds. The SDK works on all the Raspberry Pi devices. In fact, that's mostly how I use it. I use a Pi 4 to compile the code. Works on Linux, Windows, and Mac. Everything, all the SDK, all the example code is in our GitHub account. The SDK is in Pico SDK, and the examples are in Pico examples. Easy to find. Just look on our GitHub there. There's also a MicroPython port, which we really hope introduces a lot of people to the microcontroller space. This was originally developed, we did a little bit of work up front, and then it was taken over by the MicroPython devs. And so that is actually maintained by those guys now. So if you've got any really difficult questions about MicroPython, they're the people to ask. So with regard to the design of the SDK, it was designed specifically with the knowledge that the RP2040 is a microcontroller, an embedded controller. You've got limited CPU, you've got limited RAM. Most people nowadays, software guys, have never had the problem of limited CPU cycles and limited RAM. But it's a particular way of working, and the SDK is designed to try and make the best use of those resources. I can't go into a huge amount of detail. As I said, we're rapidly running out of time. So I'm not going to go into a massive sort of description of the SDK and APIs and things, but I will try and cover a couple of points that I think are quite interesting. I said we use CMake. So why do we choose CMake? Well, it's a very widely supported make system, both in IDEs and on the command line. It's easy, relatively easy to use, certainly a lot easier than defining your own make files. With a simple make list file, you can specify how your application builds, or multiple versions of your application build even. And it produces files. The CMake process produces sort of local build files, for example, that can be used by Make or Ninja or other build tools. So how does it all bolt together with regard to the code base and CMake? Well, we use interface libraries, and these actually collect all the source files, all the include paths, compiler definitions, link options, dependencies, and each sort of little library is done like that. And that means that instead of actually being libraries, they're interface libraries, they're not actual libraries, they're not pre-compiled. So when you do a build using our system, what you get is it just collates everything from all the libraries, interface libraries that have been defined or requested, and will make a single monolithic binary. But the interesting about that is because they've all been pulled in as source files rather than libraries, the compiler has a really good chance of making it extremely efficient, both in size and in speed. So that's the reason we use CMake. It's much easier to do all of that stuff in CMake than it would be in sort of things like a standard make or stuff like that. And you can customize these CMake files very easily and to get a very fine granularity on how you want your application to be built, how you want it to run, that sort of thing. So I'll really quickly whiz through this. The SDK consists of a number of layers. So we have, whilst I did say that we try and keep as close to the hardware as possible, we do have a few higher level libraries that leverage lower level functionality, things like timers, with multi-core support. There's some utility functions like print, and that's a printf and that sort of thing. These are based on the lower level libraries. We also have some runtime support libraries that, again, these pull together other smaller, lower libraries, so you can just do one library include to get an entire system that will work. We have the hardware support libraries. This is the majority of the system. This is this thin layer over the hardware I was talking about. And we also have a couple of other areas that are worth mentioning, the hardware structs library and the hardware registers. Now, these just provide easy C defines that can be used by the hardware support libraries. And these are directly generated from the register definitions in the ASIC code. Right at the bottom there, we have Tiny USB and LWIP. These are two libraries that are larger libraries, one to handle the USB that's available on the device, and the other one is for the Pico W. That's the, I can't remember what LWIP stands for now, but it's the library that is used for the wireless device on the Pico W. So that's a very quick skim through the libraries that we provide and how they're sort of bolted together. This is a very, very easy slide to talk about how to use all this stuff. you can't go through how to use all this stuff in an hour. So I'm just going to point you at our data sheets. I'm getting started with Pico PDF. As I said, we got quite a few plaudits when the device first came out just over a year ago, I think now. And I think we produced some pretty good documentation. So I'm just going to say, if you want to use this, you're going to have to read the documentation. And it's good documentation. It's easy to read. I don't want to go into any more detail in that, but I will now move on to a subject that did come up in one of the questions that was asked. That's not the slide I was expecting. Hold on a second. I think I pressed the button twice. There we go. Here we go. So one question that does come up a lot is, how do you debug these things? I see people still out there saying, well, you have to press a button to boot select and you can't debug and that sort of thing. But in fact, we've had full debugging facilities and the associated paraphernalia since the device was released. You can use a Raspberry Pi or indeed another Pico to debug a Pico. And how do we do that? Well, we have something called serial wire debug. This is an ARM protocol, 3 wires that connect from the, in our case, we'll talk about the Pico, but the exported from whatever board you're using, that you can bit bang from a Raspberry Pi. You can actually use another Pico that provides, with some Pico, you run the Pico Pro firmware, and that will allow you to plug your debug Pico, as it were, into a USB socket on your laptop or something. You can run OpenOCD and GDB on that device, and you get debugging directly onto the RP2040. This is also a great way of getting code onto the board, even if you don't use it as a debugger. But if you're fed up with pressing the boot select button and doing the mass storage device copying of the UF2 files, the sort of resulting binary from our builds, you can use either a Raspberry Pi or another Pico to actually download directly to the board without having to go through that process. And that's been available since the device was first released. Okay, so what do we got here? We're looking at how do we design these things. Again, I'm going to refer you to our documentation. There's just too much to go into in a short talk like this. Again, we've got the data sheets. We've got a specific hardware design document that will take you through how to incorporate an RP2040 onto your base board. We have, as we referred to earlier, the minimal board design. That's available for KiCad. We have a VGA board design, which is a sort of resistor ladder of an interface to provide VGA output from an RP2040. If you're interested in the RP2040 and building it into a product you might have, but don't have the experience to do it, we do run a network of design partners. Again, available on our website is information on how to get in touch with those. These are people who have a lot of experience designing Raspberry Pis into third-party products. So it's well worth talking to those guys if you have questions or you have a product you want to build an RP2040 but don't have the in-house ability to do so. I'll note at this point that we don't have the in-house ability to do that either. We have the knowledge, but we don't have the staff. We're a very busy company, and we have engineers working full tilt on new products all the time. So we don't have the time to design other people's products for them, no matter how much money you offer us. And so that's why we have this design partner network. If you're moving to an RP2040 from another device, there's a few sort of caveats to look into. I know a lot of people have moved to the RP2040, not necessarily because of its feature set, but because they can't get hold of other devices. But once they get hold of the RP2040, they find out, actually, this is a pretty good bit of kit. So there's a few things you need to ask yourself. Are there enough interfaces? 2I2C, 2SPI. But don't forget the PIO, which dramatically increases the amount of interfaces you can stick onto your hardware. Do you have the right power supplies? Do you have the right memory? If you're coming from a device that has inbuilt memory, then you're obviously going to have to redesign your board to take a QSPI flash. That's well worth considering if you're considering the RP2040. Does the device have enough speed compared with your old core? Well, almost certainly. I mean, if you go back to our comparison table earlier, you see we were running at considerably higher clock speeds than many other competitors. So almost certainly you're going to be able to perform to the required level. What about the software? Well, the SDK is our own API, so that's not on other products. So if you're going to move to us, then you are going to need to do some software work. We like to think the SDK is quite easy to use. I've used it a lot, and I find it easy to use. But then I presume I'm quite biased. But if you are coming from something like an Arduino or whatever device, or the Atmel devices or whatever, there's certainly Arduino has been ported. The IDE has been ported to actually produce RP2040 code. So if you're coming from that neck of the woods, then it's quite possible that you're already you've got quite a head start there. And again, I've put a link to the design partners on there again. Really useful if you need to, if you don't have the in-house experience to do this, just approach our design partners. So I've talked a bit about the SDK, but what else outside of our software ecosystem is available? As I just said, the Arduino IDE is functional. There's also CircuitPython, which is Adafruit's specific MicroPython port that works on the RP2040. And there's also a number of RTOSes that have been ported and work quite well. I've just spent some time building all these and making sure they work. And the ones I got working were FreeRTOS, NutX, RTThread, and Zephyr. I think there are others out there. FreeRTOS is obviously a very, very popular real-time operating system. So that's certainly one in my testing worked really, really well. Platform IO is out there, but there's a load of others. Oh, I'll go on.
Oh, sorry. Yeah, the delay's a little funny. I feel there's one very targeted question from Jan, one of our top members. In the free RTOS port, low power tickless isn't supported yet. Is that on the radar?
We internally don't do any support for these third-party systems, so I suspect that would be something you'd have to ask FreeRTOS. We're more than happy if the FreeRTOS devs have questions on how to do it, then we're more than happy for them to come to us to ask them. But
thank you very
we
much.
don't do these third-party products, so I can't answer that question because I just don't know what they're up to.
Thank you.
One question that does come up is things like what other compilers can I use? So for example, we use the Keel compiler or we use the IAR compiler. Keel is backburnered at the moment. If you're interested in that, you'd need to talk to ARM themselves because there's some stuff going on there that I can't talk about. IAR is in progress, and we're expecting them to be able to have something in their sort of quiver, as it were, in the relatively near future. But that's down to them again. And I think I'm about to run out of time, so thank goodness it's the last slide. I hope I haven't been too quick for everybody, but and you found it interesting. But everything I've linked to or talked about is available in our data sheets. Use our forums if you've got questions. Use the Element 14 forums if you've got questions. Technical questions from industrial customers, we're more than happy to answer on applications@raspberrypi.com. And to be honest, if you really need a quick answer on something, then that would be worth trying anyway, even if you're not industrial. So also, for example, if you've got a bit of feedback on the Pico, on the RP2040, it's always useful to have that sort of stuff. Obviously, we have an ASIC team here. They're not sitting on their bottoms twiddling their thumbs. They're all working pretty hard, so we need to keep them fed with ideas. Right, so Q&A. I'm afraid I've taken up more time than I was expecting. I think we've got 1 minute and 15 seconds before the hour is up, but I'm here. I can stay as long as you need. So if you've got any questions, please let rip.
We do. We have quite a few. So you're going to have to tell me when your time is up, because we have a lot of people that are very interested in stuff. So first off, people are asking about the slides. I'm going to make the slides available so you can click on all those links on the event page. So just refresh the original event page that you were on the Element 14 community, and you can click on all the links in James's presentation. We have a bunch of questions about securing firmware, so I'll just round them up about it from Shabazz here, which any way of securing firmware at the moment on the RP2040.
Okay, so there is no OTP or no secure zone or anything on the RP2040 at all. This was a deliberate design decision. We could have put it in, but it would spend another year trying to develop the chip. So at the moment, there's nothing in there. So what we recommend is use some sort of TPM attached. At the moment, we don't have any example code or design, PCB design stuff for that. I suspect that will be fixed in the relatively near future, but I can't give you a schedule on it.
Thank you. You even answered Shabaz's follow-up question there about a TPM chip. So there you go, Shabaz. That's your answer for that one. Let's have a quick look. So you did mention Platform IO a minute ago. So Donna asks, is the SDK available in Platform IO to make updates and version control between the application and upstream SDK versions easy? If not, are there plans to publish Platform IO packages?
That obviously is more of a Platform IO question. I know we've been in contact with them and we're talking to them all the time, but I don't know the answer to the question. All I can say is that we are talking to them.
That's a fantastic answer. Alexander asks, is all the software around RP2040 open source? And what licenses of the software, GPL, MIT, or something else? So
I can't. Yeah. It is all open source. I can't remember which license it is, but it's a very permissive one. I think it was one of the MIT ones, is it? Or is it BS? No, it might be BSD2. I can't remember. It's one of those, but it's a very good. It's a good license. It's not a copyleft license, so you are free to do with code pretty much what you want. I think there's some obviously some copyright type of message you might need to put in. With regard to the documentation, that is a CC no derivatives at the moment. So whilst you can read the documentation, you can't make alterations to it.
Okay, thank you very much. I'm going to condense a couple of questions here. There's a couple of people talking about communication between the M0 cores. So I'll just go with Martin's question. What about some kind of thread API so both cores can be used? A bit more of a suggestion.
Right, well, we do provide something in the SDK to start stuff up on the other core. I'm not quite sure what FreeRTOS does with regards to how it manages that and how it does the stuff between cores. From our point of view, we provide the functionality to basically start up stuff on the other cores, but we also provide API functions for communications over the FIFOs and event systems between the two cores to make sure you keep them in step or make sure they don't trample over each other.
Okay, thank you very much. I'm just reading through some of these questions. Internal bus connector. Yep, so that one's pretty much what we've just answered. Well, that's a quick answer for you. There is, are there any other plans for variants for the RP2040?
Yes.
And there we go.
With the way that the naming scheme works implies that there may be some other products in the pipeline. I have no idea which particular products might come out or when they're scheduled to come out. But obviously we look at this all the time and we decide what the market actually wants. So yeah, like I said, we're not sitting on our hands twiddling our thumbs.
Jan, who asked one of the questions earlier, one of our top members of 14, is absolutely plugging their own blog series here, which we love. FreeRTOS does support multi-core out of the box. I'm writing a series about it on the Element 14 community. So, yeah.
Excellent. Great news.
Jan. Look forward to reading it.
We think it's fantastic that so many people have taken on board the RP2040 and so many people are working on it. It's been brilliant.
We've got a couple of quick ones. Emmanuel asks, so what is the best assembly language for the RP2040?
Oh, well, it's ARM, isn't it? It's going to be ARM. It's an ARM processor, so that's what you're going to be using. It's a strange question because there is only one assembly language, and that's ARM, so ARM assembler.
Thank you. Well, there we go, Emmanuel. Thank you. I believe that's Ernie, says in the documentation somewhere it mentions it can interface to an 8-bit data bus, I believe through PIO, but there's no example code. Any chance that there'll be example code available? Don't know how well I've worded that one for you there.
I don't know the answer to that.
Okay.
The problem we have at the moment is not enough people and too much work. So doing examples of great complexity can be a bit of a problem at the moment. We're extremely busy. I mean, a lot of people don't realize how small a team we are at Raspberry Pi. The software team that worked on Pico that did the SDK was 4 people.
Wow.
And I was one of them. But the actual ASIC team was probably another 5, if that. So, yeah, we're a very small team and spread quite thinly at the moment. So we do examples when we can. I suppose it's the best answer I can give for that.
Makes sense. One thing, just personally, I have to say the documentation's always pretty fantastic. We're working for the Element 14 community. We see a lot of, controllers, products coming through that we get to test in our road test program, which you can always check. And some people do have problems where they have a fantastic product and the documentation is lacking. So it's wonderful to see the quality of documentation that comes out of Raspberry Pi, like just always. So
well, it's great,
whoever's ego needs fluffing for that, there we go. Okay. I'll give you a couple of quick, just a couple more before we start wrapping up. So anybody with any burning questions now, feel free to add them into chat, or you can comment on them on the event page underneath, and we'll make sure that we communicate any suggestions or whatever through to James after. Do you have a library where I can use the RP2040 to program other microcontrollers without a Pico probe, just SPI to SWD communication?
Not that I'm aware of.
Okay.
We basically just use a Pi, bit-banged Pi I use a Pi to bit-bang over SWD and use OpenOCD on top of that, and then GDB over the top of that. I've not used the Pico probe, but because I just use the Pi all the time. I'm not sure whether, presumably somebody's thinking of just doing it via SPI, bit-banging over SPI or something like that. And the answer is I don't know. Nothing that I've heard of.
Thank you very much. Robert asks, is it possible to program the RP2040 via the Arduino IDE?
Yes, as far as I know, it is, yeah.
Okay, thank you very much. A self-serving one here from Erin, which I love. Great and awesome introduction webinar for the RP2040. Out of nowhere question, where can I get this giant Raspberry Pi giveaway listed on the resource list? So if the link isn't working, I'll check it after the event. If not, I will make sure we connect it on the event. For James's mind, we're giving away a 4.5, 5 foot working Raspberry Pi 3 model that we have, and we're looking for the people with the best use for it that we're going to send it to. And there's just basically tell us where you're going to put it. We want it to go to a good home, and it's a giant 4 foot, 5 foot Raspberry Pi 3, which most of the GPIO pins work as well, which is pretty cool. So yeah, that's some of the strange stuff that comes out of the Element 14 community, and we love it. Thank you, Erin, for that. And I'll just wrap up with one final one. Is the RTC clock derived from a separate clock or from the master clock, says John Alexander?
Ooh, that's a tough question. I think it's derived from the master clock. But I have a vague recollection that might be able to do that, or I think you might be able to specify which one it uses as clock source, but I'm not sure. But can I refer you to our excellent documentation? Fantastic.
Okay, so we still have well over 30 questions at the moment, so I'm going to wrap up. James, it's been a pleasure having you today. I really enjoyed it. This is the second one of our Raspberry Pi webinars, and we've really enjoyed it talking about the RP2040. For anybody else that's joining, you can or if you missed some of this, this will be available on VOD on the same link, video on demand, on the same link you used to get here. So please send it to your friends and colleagues. James, thank you very much for joining us today. I really appreciate it.
Well, thank you for the opportunity. It's the first one of these I've ever done, so I hope it went well.
It was fantastic. I really enjoyed it. But yeah, any more questions, anything, any suggestions, please post it on the event. And yeah, I'm going to wrap up now. So thank you very much, James. And thank you to everybody that attended. Have a great day all.
Yeah, thanks everyone.